Hello, so this is video number 3 of section 5.3. Didn't work as well as I'd hoped. So here we are going to basically just go over two theorems that, given the examples we looked at last time, kind of just describe, I think, some of the patterns that you may have seen going through those examples corresponding to video 2. And then we're going to work through some theory problems. So we'll have a sometimes true statement, an always true statement, and we'll kind of work through proving each of those. So, Theorem 6. I think I actually did mention Theorem 6 in a previous video, but we'll state it formally, that an n by n matrix with n distinct eigenvalues is always diagonalizable. So I'll give sort of a hint as to the proof. I'll leave the proof as an exercise for you. But remember, every eigenvalue, or every distinct eigenvalue, has at least one eigenvector, and eigenvectors corresponding to distinct eigenvalues must be linearly independent. So using all of that, you should be able to prove Theorem 6, and using Theorem 5 from last video. But so we know that, of course, then, if I've got like a 3 by 3 matrix B here, and notice 3 is an upper triangular matrix with a diagonal 4, 1, negative 3, that B must be diagonalizable by Theorem 6. So since B has eigenvalues 4, 1, negative 3, being an upper triangular matrix, we know that B has 3 distinct eigenvalues. It's a 3 by 3 matrix. Therefore, by Theorem 6, it must be diagonalizable. So Theorem 6 is very nice. Theorem 6 tells us, again, if I've got just like a n by n matrix and I find n distinct eigenvalues, then it's always diagonalizable. And so that can sometimes answer the question for us very quickly if all we want to know is the matrix diagonalizable? But what if it doesn't have n distinct eigenvalues? That's where Theorem 7 comes in. So Theorem 7, we're going to let A be an n by n matrix whose distinct eigenvalues are lambda 1 through lambda p. So a little bit of sort of just notes about this before I go into these conditions. So Theorem 7 could still apply if P was actually equal to n. So, if I had n distinct eigenvalues, all of Theorem 7 would still apply fine. Theorem 6 is basically just a more concise way of writing Theorem 7. However, Theorem 7 definitely leaves the door open for the possibility that P is anything from 1 to n minus 1. So here, again, this is considering the possibility, like we looked at the end of last video, that I've got an n by n matrix with less than n distinct eigenvalues. So if you remember last video, we looked at a 3 by 3 matrix that only had 2 distinct eigenvalues. So what this theorem says is that for all k from 1 to p, so basically for each eigenvalue, first things first, the dimension of the eigenspace corresponding to lambda sub k is always less than or equal to the multiplicity of lambda sub k. So what does 1 tell us? Basically, 1 tells us that the number of linearly independent eigenvectors corresponding to any specific eigenvalue is always less than or equal to the multiplicity of that eigenvalue. And remember, multiplicity was how many times did that eigenvalue show up as a root in the characteristic polynomial. So remember, for example, if my characteristic polynomial was, say, lambda minus 1 squared times lambda plus 2, well, here lambda equals 1, right, because 1 is a root of this polynomial, would have multiplicity 2. Lambda equals negative 2 would have multiplicity 1. So what this is saying is that the number of linearly independent eigenvectors corresponding to any particular eigenvalue is always less than or equal to the multiplicity of that eigenvalue as a root in this polynomial. So for example, 1 could have up to 2 linearly independent eigenvectors associated with it, but negative 2 could only have 1 linearly independent eigenvector associated with it. All right, so 2 A is diagonalizable if and only if the sum of these dimensions is equal to n. So what that means is that A is diagonalizable if and only if the number of linearly independent eigenvectors for each eigenvalue is equal to the multiplicity of that eigenvalue. So again, if this was a characteristic polynomial of just some matrix, the matrix would be diagonalizable if and only if the eigenvalue 1 had two distinct eigenvectors corresponding to it, and the eigenvalue 2 had one distinct eigenvector, or two linearly independent eigenvectors, should say, corresponding to 1. And 2 is basically just restating theorem 5 from last video, that the matrix is diagonalizable if and only if it has n distinct eigenvectors. But because we know 1 here, we also know basically if I have less than n eigenvalues, basically which eigenvalues should correspond to more than one linearly independent eigenvector, right? So if you look at the dimension of the eigenspace corresponding to that eigenvalue, when should that dimension be greater than 1? Well, specifically if the multiplicity of that eigenvalue is bigger than 1. And then finally, 3 isn't actually really stating anything super new, but it's a good note to have moving forward, that if A is diagonalizable, then the eigenvectors of A form a basis for Rn. So if it has n distinct eigenvalues, always diagonalizable. If it has less than n distinct eigenvalues, you have to make sure that the dimension of each eigenspace, or if you prefer, the number of linearly independent eigenvectors corresponding to each eigenvalue, is equal to the multiplicity of that eigenvalue as it appears in the characteristic polynomial. So, like I said, I've got a couple theory problems on the worksheet that I just want to go through. I would highly encourage you to look through these on your own before watching the videos or watching the solutions for these, just for the practice. But so we want to show that the statement, which is number 1 here, if A is invertible, then A is diagonalizable. So we want to show that this statement is sometimes true. So this is one of those that if we want to show this is sometimes true, we should actually basically find a matrix for which this statement is true and a matrix for which this statement is false. And with most of these, we can do this using 2x2 matrices. So notice, if I just look at the identity matrix, it's kind of cheating in a way, but it works. This matrix is technically diagonalizable because it is itself a diagonal matrix, and it is also invertible because it is its own inverse. And so this is a matrix that is both invertible and diagonalizable, but I think we've actually seen this matrix here. And this matrix, and a lot of these like true-false questions concerning eigenvalues will pop up a lot, because this is a invertible matrix. We know that it's invertible because it doesn't have a zero eigenvalue, because it's row-reduced echelon form, has non-zero entries on the diagonal, a variety of reasons. But we've also seen that this matrix is not diagonalizable. Again, specifically because it has one eigenvalue of 2, which has multiplicity 2 in the characteristic polynomial, but there is only one eigenvector corresponding to 2. All right, so last statement. We want to show that this statement is always true if A is diagonalizable. Then so is A transpose. So if I wanted to convince myself that this was always true, I would need some sort of proof to accompany this statement. And generally, when we want to come up with proofs for statements like this, we always want to start out with, what do we know? we know that A is diagonalizable, right? Meaning we know that A is equal to P times D times P inverse, where P is, again, just an invertible matrix, and D is a diagonal matrix. Well, actually, we do know a lot more about P, right? That it has the eigenvectors of A, and D has the eigenvalues of A. So I think using our knowledge of diagonal matrices, transposes, and inverses, we should be able to find a similar result for A transpose by starting with this, right? Because we want to get with A being diagonalizable, or we want to start with A being diagonalizable, and we want to wind up at A transpose is diagonalizable. So what I'm going to do is I'm going to take the transpose of both sides. Well, remember, the transpose I can distribute it across these matrices as long as I just switch their order. All right. Well, remember the transpose and inverse can just swap places, right? So P inverse transpose is equal to P transpose inverse. D is a diagonal matrix. And remember, when taking the transpose, everything stays fixed, or the diagonal entries stay fixed and everything else swaps. But in a diagonal matrix, everything else is 0. So here I just get D. Oh, and then this is just equal to P transpose. And so notice I've diagonalized A transpose now using the same diagonal matrix D and the transpose of the original matrix P. So sometimes true, we want to look for these sort of cases going one way or the other. Always true, if we think it's always true. We should come up with some sort of proof like this where we kind of show in general that this has to be the case. So that wraps up section 5.3. Next section, we will move into 5.4, where we talk about kind of how we can apply all of this to linear transformations.